Hello everyone. Today I'll be presenting on grinding operations, machines and processes. What I want to focus on is not just how these processes work, but more on practical side, when to use each method, what are the trade-offs, and how engineers decide between them on the floor. Cylindrical grinding is the process of grinding the external surface of a cylindrical workpiece. The workpiece rotates on its own while the grinding will engage it. The workpiece moves back and forth laterally to cover the full length being ground. It operates by the workpiece is held by between centers rotating against the grinding wheel. The wheel is dressed to either a flat profile for standard diameter grinding or to a formed profile if you need complex shapes like threads. So the operational intent to produce accurate round components. The pros is excellent roundness and diameter control, can handle large diameter rolls and complex form profiles. But the limitation, it requires workpiece rotation and precise alignment, lower throughput than centerless grinding for mass production, and its best choice for precision shaft rollers, crankshaft journals, threaded components, and large industrial rolls. Internal grinding is essentially the same concept but applied to the inside of a bore. A small grinding wheel is mounted on a spindle and inserted into the bore to grind the internal surface. Because the wheel must fit inside the bore, it is necessarily smaller than the bore diameter. The wheel rotates at very high speed to compensate, and it needs higher RPM to maintain the required surface speed. The workpiece typically rotates in the opposite direction to the wheel. So the operational intent to achieve high accuracy internal surfaces and bore geometries that cannot be reached by external grinding methods. The pros, it produces highly accurate bores and internal profiles, enable precision finishing of hardened internal features. But it also wear out faster, access limitation, reduce productivity for deep cavities, and it is mandatory for bearing races, hydraulic cylinders, precision bushings, and internal gear related components. Centerless grinding grinds cylindrical surfaces without mounting the workpiece between centers or in a chuck. Instead, the workpiece rests on a support blade held between the grinding wheel and a smaller regulating wheel. The regulating wheel controls both the rotation speed of the workpiece and its speed rate through the machine. The grinding wheel does the actual material removal because there's no chucking or centering involved. Parts can be fed continuously through the machine. This is called through feed grinding. So the intention is to maximize the production throughput for cylindrical components without using centers or chucks. It is extremely high production rate, eliminates work holding setup time for many parts, but it is less flexible for highly complex geometries. Process setup and regulation can be challenging. So it is ideal for manufacturing large volumes of pins, rod shafts, fasteners, and automotive components. Creep grinding is a heavy-duty variant of surface grinding, where the wheel takes a very deep cut while the workpiece moves extremely slowly. Conventionally, grinding uses many shallow paths at high workpiece speed. Creep feed does the opposite, one or very few deep paths at very low speed. The wheel is usually a soft grade resin bonded wheel with a open structure to allow coolant penetration and chip clearance across the large contact area. It is capable of removing large volumes of material in one pass, produces accurate complex profiles that would otherwise require multiple milling or broaching operations, and excellent surface finish on difficult materials. But the high wheel wear rate due to large contact area, requires significant coolant supply to manage it, slower cycle time per pass compared to conventional grinding. So it best applied to aerospace turbine blades, forming tools, and any hardened component with intricate contour profiles where conventional milling would struggle to hold tolerance. Hardening is the use of a single point cutting tool, typically CBN or ceramic, to turn hardened steel directly without grinding. It emerged as a potential alternative to cylindrical grinding for finishing hardened components. The operation involved the workpiece spin on the lathe and a very hard cutting remove material in the conventional turning manner. The key difference from regular turning is the workpiece hardness, typically above 45 HRC, which will destroy conventional tooling. So the grinding offers superior surface finish consistency, better support for large slender and flexible workpiece, but also higher machine and operating costs, greater energy consumption than hard turning. The hard turning also lower energy consumption compared to grinding, and no grinding wheel uh, or dressing costs, but it also lower precision and accuracy, rougher surface finish, and struggle with long thin workpiece. So the decision between the two usually comes down to volume, required surface integrity, and whether the workpiece geometry suits turning. Beyond dedicating grinding machine, there's a whole family of tool variant designed for different work environment and scales, from precision tool room used to heavy foundry work and field maintenance. Universal tool and cutter grinders, highly adjustable machine used in tool rooms to sharpen and recondition cutting tools like end mills, drills, and lathe tools. Precision is their defining characteristic. Swing frame grinders, a large counterbalance unit suspend on a pivot frame. The operator swings the heavy grinding head across large casting to remove flash, gates, and surface defects, built for endurance and reach with not precision. Portable grinders, handheld units, either electric or pneumatic, used for deburring, weld dressing, and surface cleanup in any location. Pneumatic versions are preferred in environments where sparks near electrical equipment are a concern, and bench and pedestal grinders, fixed workshop grinders used for routine of hand sharpening of drill bits, chisels, and small tools. Every workshop has one. The key principle is matching the tool to the environment and the scale of the job. Grinding generates heat through friction between the abrasive grains and the workpiece. If this heat isn't managed, it causes thermal damage, surface burns, microstructural changes, residual tensile stresses, and dimensional distortion. Grinding fluids are typically water-based emulsion for most operations, or straight oils for thread grindings are applied at the grinding zone to cool the workpiece, lubricate the contact, and flush chips away from the wheelpiece. It improves surface finish and dimensional accuracy, reduces workpiece temperature, and extends wheel effectiveness. But on the other hand, fluid handling and disposal increase operating costs. Improper fluid selection reduces effectiveness. So it is critical for precision grinding of hardened steels, thread grinding operation, and any process where thermal distortion could cause scrap or rework. Grinding cattle occurs when vibration disrupt the grinding process, leading to poor surface finish and dimensional inaccuracy. Identifying root causes is essential for achieving optimal grinding performance. To prevent cater, we have to inspect bearings and spindle condition, check wheel balance and wheel uniformity, evaluate wheel wear and bracing practices, improve workpiece rigidity and support, reduce material removal rate if necessary, and verify external vibration sources. That is all from me. Thank you for listening.